The reason for that is because, well, group 8A normally do not participate in chemical reaction. There are noble gas elements there, so we don't really need to worry about those. Okay? If you look at this picture, within the same group, top to bottom, bigger and bigger, left to right, smaller and smaller. That, again, has something to do with the effective nuclear charge. Effective nuclear charge is decreasing from top to bottom, meaning the valence electrons are further away from the positively charged center. As a result, the size is increasing. Now, within the same period, you have more electrons packed on the same level. They are being closely held closer, and they are being held closer to the positively charged center. As a result, you see the shrink in size. Okay, so from top to bottom, the size is increasing within the same group, left to right, within the same period, and size are decreasing. Okay, so and again, increasing in effective nuclear charge, resulting in a shrinking size, decreasing in the effective nuclear charge from top to bottom within the same group, resulting in an increase in size. But another reason you may think of is that period 1, period 2, period 3, period 7, as the n number goes up, the energy of the electron in those different shells is going up, meaning those electrons can move further away from the positively charged center. As a result, the size is getting bigger, because essentially the size of the atom depends on how far away the electron can move around. The size of the solar system depends on the boundary of the solar system. Okay, and Mercury and Mars and Mercury were closer, and Earth were closer to the sun, and Jupiter and Saturn, they are further away from the sun. So the size of the solar system is not dependent on how close we are on Earth to the sun. Rather, it's something beyond us and further away from the size from the positively charged center. Yeah. So in that sense, when you have increase in the period number n equals 1 through n equals 7, that means you are going, as you increase in n number, the distance is increasing. As a result, the size is getting bigger. Okay, so that's the general trend in the atomic size there, atomic radii there. Increasing top to bottom, increasing right to left. But if you're talking about left to right, well, that's a decreasing in size there. What about the periodic trend, or the ion? Since we're dealing with the atoms there, well, the atoms are reacting with other atoms and forming the ions there. So we want to take a look at the size of the ion. How do we determine the size of the ion? What's the general trend in terms of size of ion? Well, when you talk about the ions, you have to differentiate between the positively charged ion and negatively charged ion. If the positively charged ion, you are losing electron. Negatively charged ion, you are gaining electron. In general, we say for the positively charged ion, the size is getting smaller compared to the atom that they come from. That makes sense. Sodium, you have 11 electron, 11 proton. They are attracted to one another. If you remove one of the electrons, you form the sodium ion. You have 11 protons. You only have 10 electrons. So the attraction becomes stronger. As a result, the size is smaller. We can actually calculate the actual number in the based on the experimental data there. You can see sodium atom, the radius is 186 picometer. Ion, 116. Same thing happens to calcium, the 197 versus 114. So the ion, the positively charged ion, the size is getting smaller comparing to the atom that they come from. Negatively charged ion, the size is getting bigger because negatively charged ion, you are gaining electron. You have the same number of protons, but this time you have more electrons, resulting in a not as a strong attraction of those acquired electrons there. As a result, you see the trend. 100 picometer for the size of the chlorine atom there, 167, almost 70% increase in size in terms of the size of the ion compared to the size of the atom you come from there. So for the formation of the cation there, and this is an example, lithium, using lithium as an example, you start with 3 electrons, 3 protons, okay, and the size is 152 picometer. if you take one of the electron away, you only have 2 electrons but 3 positive charge, 3 photons there. The lithium ion has 78 picometer as a radius. So in this case, when you form an cation there, the size gets smaller comparing to the atom that it comes from, and this is because the electron-proton attraction has gone up, so the size decreases. Okay. Now for the negatively charged ion, using say fluorine as an example, you have 9 electron, 9 proton. Okay. Now the formation of the fluoride ion, you result in 9 protons. You have changed the number of protons there, and 10 electrons. In this case, the size is getting bigger. Anions are larger than the atom from which they come from, simply because the electron-proton attraction has gone down. Therefore, the size increases. Okay. So when you talk about the size of the ion, radius of ion, well, you have to differentiate between the 2 different types of ion. But in general, the dotted line on the left side of this slide, the dotted line represents the size of the atom. The solid color purple dot represents the size of the ion. The size of the ion for positively charged ion is smaller than the atom, but it still follows the same pattern. From top to bottom, the ion is getting bigger and bigger. The atom itself is getting bigger and bigger, so when you lose that same number of electrons there, the ion form is still going to have that same trend. On the right side, though, the dotted line represents the size of the atom. The solid color represents the size of the ion. You can see the ions are bigger than the size of the atom here. That's something that we need you to memorize. And talking about, I'll probably take another couple minutes there before we wrap it up for today's class there. And talking about the periodic property, one more thing a couple more things we want to introduce here is the metallic character of the element. Now the metals will lose electron to form cation, non-metal will gain electron to form anion. That's what we talked about since the beginning of the semester here. Now the metallic character, how do we define metallic character? Metallic character is how closely an element's property matches the ideal property of a metal. So if you have a metal by definition is something that easily loses an electron. Now, each metal is different, each element is different. If you have a particular element that is very easy to lose electron, we'll say, well, this particular element has a stronger metallic character. If it going from left to right, it becomes more and more difficult to lose electrons. Well, it has less metallic character. So that's how we define metallic character. Okay. Now, metallic character is increasing from top to bottom. Now, group 1A element is a perfect example. Hydrogen is not even a metal. Well, lithium, sodium, potassium, those are metals. So, non-metal transitioning into metal. That's an increasing in metallic property. Okay. The metallic character is decreasing going from left to right. It's very easy to see that. Lithium is metal, beryllium is a metal, and then you go here, carbon, nitrogen, oxygen. We're getting into non-metal. Metal to non-metal, the metallic character is decreasing. So that's the general trend. Going from left to right, things are getting non-metallic. Going from top to bottom, things are getting more metallic. Okay, so this is the trend there. Now, within the same group there, you can also say